Hello, hi. In this video, we are going to discuss how to design an analog Butterworth low pass filter. Okay, so in order to design analog filters, we have two methods. One is Butterworth, another one is Chabezu. Okay, in the Chabezu again we have two techniques, Chabezu type 1 and type 2. But in this video, we will discuss how to design an analog Butterworth low pass filter. First, we will discuss the steps to design an analog Butterworth low pass filter. Then we will discuss one problem. So, steps to design an analog Butterworth low pass filter. First thing, from the given specification, find the order of the filter. That is, you have to find out the n value. Round off it to the next higher integer. Usually you will get in the decimal value 3.9, 4.9 like this. You have to convert it into or round off the obtained value into a next higher integer value. Third step is find the transfer function h of s for the cutoff. This is a normalized cutoff frequency 1 radian per second for the value of n. Okay, so for the you have determined the order of the filter n, right? So by using that value, you have to find out the transfer function for the normalized cutoff frequency. This is a analog cutoff frequency. The unit is radian per second. If it is digital frequency, the unit is hertz. You know very well all those things, right? So the fourth step, how you can find out this transfer function? Here we have one table. You have to memorize that table. Here I have referred P. Ramesh Babu book. It is a digital signal processing 7th edition. Okay, in that book, table 5.1, that is in the page number infinite impulse response filter 5.9. So in that page, you can see the table 5.1 list of Butterworth polynomials. This is the table. Okay, this is the table 5.1 list of Butterworth polynomials. So I will show you. I will discuss how to write, how to utilize this table. Usually, you have to memorize this. Memorize this table. Okay. So without this table, you can't write the transfer function. Actually, these are the one part of the transfer function. Actually, what is the transfer function? Transfer function is the ratio of h of s. h of s, it is an analog transfer function, right? h of s is a ratio of numerator divided by denominator, right? So here we are going to use these polynomials based on the order of the filter. Here n is the order of the filter, 1 up to they have given 7. Usually they will give up to 4. Please memorize these polynomials for up to at least for the order of the filter 4. Okay, so here you have to use this denominator polynomial. So what is the value of numerator, ma'am? The numerator value is 1, or for all the problems the numerator value is 1, the denominator value is, you have to write for the order of the filter n is equal to 4, you have to write this equation, polynomial equation. Okay, so the fourth step is calculate the value of cutoff frequency. This is the new cutoff frequency. Here we have taken the transfer function for the order of the for the cutoff frequency. This is normalized cutoff frequency 1 radian per second for the determined value of n, order of the filter, right? Here we have to find out the new cutoff frequency. Okay, the fifth, the last step is Find the transfer function. It is a, what is the subscript of A is, it is an analog. H subscript A of A is, it is an analog transfer function for the above value of, for the determined cutoff frequency, not for the normalized cutoff frequency, for the determined cutoff frequency by substituting. How can we find out? It is a design of uh, analog Butterworth low pass filter, right? So for this one, it is or we can also say it is a Butterworth type of filter design. For this one, wherever we will see the S, we have to replace S divided by omega C in the transfer function. Okay, so now we will discuss one problem. Okay, you will get this problem for 7 marks for in your exam. Okay, design an analog Butterworth filter that has a -2 decibel pass band attenuation. Okay, at a frequency of 20 radian per second, and at least -10 decibel stop band attenuation at 30 radian per second. Have you understand this problem? If you are not understand, I will explain you in detail. Okay, so actually you can actually it is a design of low pass filter, right? So it is a design of low pass filter. The This is the graph of magnitude response. We have two response, right? Magnitude response and phase response. We can also call these two responses as a frequency response, right? In the frequency response, we have two responses. One is a magnitude response, another one is a phase response. Here we are going to discuss magnitude response. This is the magnitude response of low pass filter, right? So this is the magnitude 1 usually. Okay, and this is the stop band, this is the pass band attenuation. Okay, this range is pass band attenuation. Okay, here we will get stop band attenuation. What is this? This is a stop band attenuation. Here we will see the frequency. Okay, this is the pause okay, attenuation. We are usually use the for attenuation alpha p. Sorry, this is alpha s. For cut for frequencies, pass band frequency, for representation we will use this symbol. Okay, we will see, we call this one as omega, right? For analog, we will represent using this one. It looks like a unit of resistance, right? Ohm, right? So this is a pass band frequency. This is a stop band frequency, isn't it? This is a alpha p, means it is a pass band attenuation. It is a stop band attenuation. This is a pass band frequency. It is a stop band frequency. Okay, so usually the attenuation we will use the unit decibel, right? So solution, first step is you have to write the given specification. This is the pass band attenuation. They have given -2 decibel. You have to use 2 decibel, that's it. No need to use that sign, minus sign. Stop band attenuation is 10 decibel, right? Similarly, you have to write pass band frequency. What is that? 20 radian per second, and stop band frequency 30 radian per second. Now we have to use the formula to find out the order of the filter. So in order to find out the order of the filter, you have to use this equation, n greater than, you have to memorize this equation. So, okay, so memorizing all the equations is very very must from the exam point of view. Okay, if you are writing any one, if you are missing any parameter or any value in the equation, even if you did problem correctly but with wrong equation, you will get 0 marks. Okay, please keep it in your mind, memorize the equations properly. Okay, and write the equation properly in your exam. So n greater than equal to logarithm of square root of 10 to the power of 0.1. This is a alpha s top band attenuation minus 1 divided by 10 to the power of 0.1 alpha p passband attenuation minus 1 divided by log of alpha, sorry, omega s divided by omega p. Okay, so thereafter, so you have to substitute the value of alpha s, alpha p, okay, and omega s, omega p in this formula. Okay, so after substituting, use the simple maths to solve this problem. Use calculator to solve this problem. Okay, so I don't want to explain in detail how to solve. It is a simple math. Use the calculator and solve. So finally you will get 3.28. So I said the second step is you have the approximate, this is an approximated value of n. So you have to change, you have to convert into the highest integer number, right? So here I got 3.38. So the our value is higher order, higher value is for this 3.38 is 4. If it is 4.48 is 5. If it is anything, just you have to write the highest value of the obtained value after solving the equation. Okay, after substituting whatever you are substituting the values in the given in the equation, right? So you will get some value, right? So in this value you have to write the highest integer value. The order of the filter is now n is equal to 4. You have to see this table. Okay, the table for the order of the filter is 4. The denominator of the transfer function is this equation. You have to use this polynomial equation in the denominator. Okay, this is your transfer function. Still we have not obtained analog Butterworth low pass filter, right? So just we have determined the transfer function. Okay, so after this is your transfer function, normalized low pass Butterworth filter for n is equal to, why I have written normalized low pass Butterworth filter, because here we have considered the normalized cutoff frequency 1 radian per second. So that's why we are using the normalized low pass Butterworth filter for n is equal to 4. So after writing this equation, so we have to find out the equation, right? Another equation is what? We have to find out the cutoff, new cutoff frequency. For that one we have two equation, right? What are those equation? This is the cutoff frequency with using the passband frequency, right? Here we have considered the only passband frequency and passband attenuation in order to determine the new cutoff frequency. Another equation is you only using stop band frequency and stop band attenuation, we can also possible to find out the cutoff frequency. Here there is no rules and condition which equation we can use to find out the cutoff frequency. Here they have given both the pass band frequency, stop band frequency, and pass band attenuation, stop band attenuation. You can use any one of the equation. Okay, here I am going to use the first equation to find out the cutoff frequency. Going to use this equation to find out the cutoff frequency. Okay, so omega p divided by 10 to the power of 0.1 alpha p minus 1 to the power of 1 by 2 n. Right, n is the order of the filter, omega p is the passband frequency, alpha p is the passband attenuation. So passband attenuation is the unit is what? Decibel. The frequency, that passband frequency is radian per second. So here we know the order of the filter n is equal to 4. Using those values, just substitute those values in the cutoff frequency in the equation 1. Okay, so omega p is 20, alpha p is 2. Okay, so order of the filter is 4, right? So these things you have to substitute in the equation 1 and use the calculator and solve this problem. Find out the cutoff frequency. New cutoff frequency is 21.386, right? 386 radian per second. Okay, so I have written here, have not written here, just make it, just don't forget to write the unit. Okay, thereafter now only we are for this given cutoff frequency, so we are converting the transfer function to analog Butterworth low pass filter transfer function. Okay, so here the last step is, this is the obtained cutoff frequency 21 point whatever we have determined the previously, the cutoff frequency, that value only I have taken here. So the next one is, so wherever we have that s, right, s is actually representation of frequency, right? So it is a time domain to frequency domain conversion, which we are using the Laplace transform, right? There we are using this symbol s, right? S representation is Laplace transform s. Okay, so frequency domain representation. Okay, s tends to s divided by omega c. Here we have determined the cutoff frequency 21.386. So we have to use this one in the transfer function. So we have determined the transfer function here, right? So we have to use this transfer, wherever we have that s there, we have to substitute s divided by omega c. The value of omega c is determined 21.386, right? Just substitute that one and simplifies this transfer function. Please don't represent like this. Simplifies this denominator equation. Okay, in this format. Okay, just solve this equation, that's all. Make it this here s square divided by 21.386 square, like this. So you will get the common number, right? So this one, right? Take this one 457.36 in the numerator and you will get this equation in the denominator. This is your final analog transfer function using Butterworth for low pass filter. I hope you will understand this problem. So how to design transfer function, design Butterworth analog Butterworth low pass filter. Okay, for the given specification. If you like this video, share my video, subscribe my channel, like my video. Thank you very much.